Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. We take big ideas about space, time, reality, and existence, and turn them into simple, soothing stories you can drift off to. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space, and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from, and what time it is for you right now, and wherever you are, maybe lying in bed, settling into the night, or just looking for a moment of calm. I hope this time feels peaceful. I hope your mind can soften, your breathing can slow, and your body can rest. Thank you for being here. Now, let's begin. Tonight, we're going to drift into a story about something truly extraordinary. A new world discovered in the far outer reaches of our solar system, beyond the familiar planets, the icy dwarf worlds, and even beyond the orbit of Pluto. A world so distant that sunlight, which warms our faces in less than a single second on Earth, arrives there as the faintest whisper of light, like a candle flickering in a cold cathedral. A world that has spent 4.5 billion years in nearly perfect solitude, tracing an orbit so long and so stretched that its full journey around the Sun takes thousands of Earth years. Its name is Ammonite. The name probably surprised you the first time you heard it. After all, ammonites are ancient marine fossils found in sedimentary rocks on Earth, spiral shells from creatures that lived in oceans hundreds of millions of years ago. They swam in a world where vertebrates were just beginning to evolve, where continents hadn't yet settled into their modern forms, and where life itself was still experimenting with possibility. To name a frozen, distant world after an ancient, spiral-shaped fossil seems strange, until you realize what ammonites really are. They are time capsules, fragments of the deep past, preserved through unimaginable stretches of geological time. They are windows into worlds long vanished. And that is precisely what this new discovery represents. Not a fossil of ancient life, but a fossil of the early solar system itself. A preserved remnant from the era when the planets were being born. A tiny shard of cosmic history, frozen in darkness since before there was an Earth to name it. Officially designated 2023 KQ-14, Ammonite was discovered by an international team of researchers using the Subaru telescope on the summit of Mauna Kea in Hawaii. This is not just a big telescope or a powerful telescope. It is a machine built to do something very specific. Detect objects so faint, so distant, and so slow-moving that they barely register as pinpricks against the cosmic darkness. Its most remarkable tool is the Hyper Suprime Cam, an instrument capable of capturing images containing nearly 1 billion pixels, scanning enormous sections of sky with exquisite sensitivity. Imagine trying to spot a single grain of dust drifting in a black cathedral the size of a continent, lit only by moonlight. That is the scale of difficulty we're talking about. And yet there it was, tiny, silent, barely perceptible, moving ever so slightly between images taken weeks apart, a ghost of a world emerging from the data like a faint memory rising from sleep. To understand Ammonite, picture something between a large asteroid and a small moon. Estimates suggest a diameter between 136 and 236 miles across, roughly 220 to 380 kilometers. That makes it larger than many dwarf planet candidates, but not nearly as large as objects like Pluto or Eris. Its size is not what makes it remarkable. Its orbit is. Ammonite belongs to a group of objects so rare that the entire solar system contains only 4 known examples. The sednoids. Sednoids are not like anything you've heard of before. They are not Kuiper Belt objects, not Oort cloud objects, not normal comets. They are, quite literally, the loneliest objects in the solar system. Their orbits do not resemble the familiar circles and ellipses traced by planets and dwarf planets. Instead, sednoids follow highly stretched, elongated paths, venturing out to distances that defy intuitive comprehension. For Ammonite, closest approach to the Sun, 60x AU, 60x times the Earth-Sun distance. Farthest distance, 252 AU, literally hundreds of times farther than Earth. For context, Pluto orbits in 40 AU, Neptune at 30 Agus. Ammonite's closest approach is already far beyond anything we typically think of as the edge of the solar system. Its farthest point is a region so cold, so empty, and so quiet that light from the sun takes almost a full day to arrive. Let's slow down for a moment and imagine this. If Earth's orbit were represented by a coin, then the orbit of Ammonite, at its closest, would be the size of a small room. And at its farthest, it would stretch the length of several football fields. And this is not a temporary orbit, not a recent event, not the aftermath of some cosmic collision. Computer simulations show that Ammonite has followed this path for 4.5 billion years, essentially the entire history of the solar system. It is a pristine remnant of a time when our cosmic neighborhood was still assembling itself from dust and gas, a witness to the solar system's chaotic youth. Finding Ammonite was not a moment of sudden revelation. There was no dramatic exclamation, no instant certainty. Its existence was built slowly, like a puzzle being assembled piece by piece. The first hints appeared in images from March, May, and August of 2023. Tiny points of light, faint and unremarkable, shifting slightly between exposures. But faintness is not proof. Motion is not confirmation. To verify this world existed, astronomers needed months of follow-up observations, measurements of its motion against the star field, confirmation from multiple telescopes. In July 2024, the Canada-France-Hawaii telescope observed it again, allowing researchers to calculate its orbit with stunning precision. And then something remarkable happened. They searched archival images going back nearly 20 years and found it. It was there in images from 2021 to 2014 and even 2005, patiently drifting through space, unnoticed. Imagine that. For nearly 2 decades, humanity had pictures of this world stored away on hard drives, burned into digital archives, but no one noticed it. Not because we are careless, but because reality is vast, and our tools are only now becoming sensitive enough to see its most delicate structures. Sometimes, the universe gives us answers before we even know which questions to ask. Analysis of Ammonite's orbit revealed something astonishing. It is not unstable, not temporary, not a chaotic survivor. It has remained on its path for billions of years, untouched by gravitational disturbances. It has not been tugged inward by the gas giants, not flung outward into interstellar space, not perturbed by collisions or migrations. It exists in a region where the solar system is so empty that entire worlds can remain untouched for geological ages. In this cosmic quiet, Ammonite has kept its secrets intact, preserving a record of conditions that existed before Earth formed, before oceans formed, before life began. It is a time capsule of unimaginable age. But perhaps the most intriguing question is, how did Ammonite get there? How did this world end up in an orbit so vast, so stretched, and so stable? And why does it not align with the other sednoids? Some astronomers believe sednoids were shaped by the gravitational influence of a massive unseen planet far beyond Neptune, the legendary Planet 9. One hypothesis suggests this planet, perhaps 4 times the mass of Earth, sculpted the orbits of distant objects, shepherding them into alignment like a cosmic conductor. But Ammonite doesn't match. It is the odd one out. Its orbit is oriented differently. Its alignment is peculiar. Its behavior challenges the model. One researcher put it this way: if Planet 9 exists, why would Ammonite ignore its influence? It's a simple, powerful question. And, like all good scientific questions, it opens a door to deeper mystery. Computer models suggest a fascinating possibility. Around 4.2 billion years ago, Ammonite and the other sednoids may have shared remarkably similar orbits. And then, something happened. Something powerful. Something disruptive. Something ancient. Perhaps a passing star drifted close to the young solar system, or a planet was ejected into interstellar space, or a massive object plunged inward and destabilized its neighbors. Whatever happened, it scattered these distant worlds into their current positions. And Ammonite somehow ended up here, frozen in time, preserved in darkness, a fossilized memory of the chaos that shaped our cosmic home. As you settle deeper into your pillow, you might reflect on the strange patience of the universe. Worlds like Ammonite were formed billions of years before humans existed. Billions of years before animals evolved. Billions of years before Earth had oxygen, or continents, or oceans. And for all that time, this world has been drifting through space, silent and unseen. Until, at last, a handful of tiny creatures on a small blue planet built tools powerful enough to notice it. Not because they needed to, but because they wanted to. Because curiosity is one of the most beautiful expressions of consciousness. We are small. The universe is vast. And yet, somehow we reach across that vastness and touch worlds that have been waiting all along. Together, we drift farther into the outer dark, following Ammonite through regions where sunlight is a memory more than a presence, where the universe moves at the slow pace of geological time. Tonight, we explore why this discovery matters, not only scientifically, but emotionally, philosophically, cosmically. Because Ammonite is not just any object. It is part of a family of 4, and until recently, it was a family we didn't even know existed. Sednoids are the rarest population of worlds we know of. There are more: planets, moons, asteroids, comets, Kuiper Belt objects than sednoids. For billions of years, they have been drifting so quietly that only the most sensitive instruments can detect them. Imagine an ocean with thousands of ships, thousands of driftwood pieces, thousands of waves. Then imagine something floating beyond all of it, barely visible in the fog. That is a sednoid. Only 4 have been confirmed. Sedna 2012, VP 113, 2015, TG387. Ammonite 2023, KQ Onditan. 4 worlds, out of billions of objects orbiting our star. Their distinguishing feature? An orbit that is so stretched, so unusual, so far beyond the gravitational influence of known planets that it shouldn't exist. And yet it does. Sedna, the first, shocked astronomers in 2003. Its path through space seemed almost unexplainable. The others only deepened the mystery. And now Ammonite has joined them. Softly, silently, unsettling theories we thought were settled. Let's slow down and imagine Ammonite's orbit. Most planets follow ellipses that resemble long ovals, but they're still somewhat circular. Ammonite's orbit is like drawing a line across a field, running off into the horizon, looping back centuries later. It floats 66 AU from the Sun at closest, then wanders 252 AU away at farthest. Nothing we know should produce a stable orbit like this. Our models say such an object should drift away, evaporate from gravitational influence, or be pulled inward over billions of years. Yet Ammonite persists, stable, predictable, ancient, like a pendulum frozen in motion, ticking out epochs rather than seconds. Why did astronomers get so excited? Because a sednoid is a message in a bottle. Other objects, near planets, near asteroid belts, near moons, have been disturbed, reshaped, scattered. But sednoids, like Ammonite, formed early, were thrown far, then never touched again. They orbit where nothing interacts with them. Not Jupiter, not Neptune, not planetary migrations, not collisions. They are pristine fossils of the solar system's formation. Their existence tells us that something dramatic happened long ago. A reshuffling, a gravitational upheaval. Something powerful enough to carve these rare trajectories. What could that something be? For years, astronomers have wrestled with a hypothesis so bold it sounds almost mythical. There may be a 9th planet lurking in the outer solar system. Not Pluto, a true planet. Maybe 4 times the mass of Earth, maybe 6 to 10 times Earth's diameter, orbiting so far away that even our best telescopes cannot yet detect it. Planet 9, as it's called, would be large enough to sculpt orbits shepherd. Small bodies align distant objects like Sedna. The idea was compelling because the first 3 sednoids all pointed the same way in space. If you dropped debris into a river with a strong current, all the sticks would drift downstream. That was the logic. Something massive must be pushing these objects into alignment. Maybe a hidden world. Cold, dark, solitary. A planet wandering the outskirts of the solar system unseen. Astronomers spent years searching, running simulations, projecting possible locations, exposing photographic plates, scrutinizing sky surveys pixel by pixel. The debate became heated, with entire research groups forming around the effort. Was this the greatest planetary discovery in modern times? Or was it simply an illusion created by the biases of observation? Then came Ammonite, a new puzzle piece falling gently into place. And suddenly, the picture changed. The first 3 sednoids shared a similar orbital orientation, but Ammonite, its orbit points somewhere else, like a child wandering away from a line of marching siblings. This immediately deepened the debate. If Planet 9 shaped the orbits of sednoids, then why didn't Ammonite obey that same influence? Either Planet 9 does not exist, Planet Nine's influence is weaker or more complex than thought. Another mechanism shaped Ammonite. Multiple mechanisms shaped these worlds differently. We are missing fundamental interactions entirely. That one faint point of light, found in digital archives and detected after decades of waiting, may have overturned an entire planetary hypothesis. Or it may have revealed something deeper, that the outer solar system's past was messier, richer, and more violent than we expected. Many theories now compete softly for attention, like voices speaking from opposite corners of a quiet room. Here are a few. 1. A passing star. When the sun was young, it was born in a cluster, stars packed tighter than in today's skies. A close passage might have pulled objects outward, stretched their orbits, scattered them. 2. A long-lost planet. Perhaps another world once existed. A planet that roamed the outskirts, nudged sednoids into place, then was flung outward into interstellar space, a cosmic exile. 3. Subtle gravitational resonance. Perhaps dozens of small objects, not one giant planet, collectively created these patterns, like ripples forming a wave. 4. Unknown physics. Maybe there are processes acting in the far outer solar system that our current theories cannot yet grasp. Each possibility is breathtaking in its own right. Each speaks to a universe that is wider, older, and stranger than it first appears. One of the most beautiful parts of Ammonite's story is how it was found not just in new images, but in old ones. Images from 1921, 2014, and even 2005. Ammonite was there, quiet, undisturbed, waiting to be noticed. This is why astronomers preserve sky surveys. They are libraries of the past, shelves full of star maps containing discoveries yet unopened. It sometimes takes decades for human understanding to mature enough to recognize what was already recorded. There is something deeply poetic in that. The universe hides its answers in plain sight and waits for us to learn how to see. Let's pause and honor the technology that revealed this world. The Subaru telescope, located atop Mauna Kea in Hawaii, nearly 14,000 feet above sea level, built to see faint objects at the edge of detectability. Atop its massive structure sits the Hyper Suprime Cam 0.9 gigapixels, 116 detectors, able to search the faintest whispers of light designed for wide-field deep surveys. This is not merely equipment. It is the culmination of decades of engineering, thousands of hands, countless calculations, quiet determination just so we can detect small worlds in the dark. And these are not just scientific triumphs. They are reflections of human spirit. We reach across the void not with rockets alone, but with patience, ingenuity, and yearning. Astronomy is rarely a solitary endeavor anymore. Ammonite was discovered by researchers from Taiwan, Japan, Canada, Korea, China, and observatories across the Pacific. Different languages, different cultures, different histories, all united by curiosity and a shared belief that knowledge is worth seeking. Through these collaborations, we glimpse the best of humanity, quiet cooperation in service of understanding. Let's rest here for a moment. Time works differently in the outer solar system. On Earth, we measure time in minutes, hours, days, years. But through Ammonite's eyes, a year is meaningless. A civilization is a flicker. A species is a passing breeze. Its orbit is so slow that written history from ancient Mesopotamia until today would amount to maybe a single inch of its elliptical path. All of human existence is but a heartbeat in its movement. this object has watched. Continents form and drift. Oceans rise and vanish, mountains thrust upward and crumble, species bloom and disappear across its silent journey. This perspective is humbling, yet strangely comforting. Because if a world can exist for 4.5 billion years doing almost nothing but being, then maybe you, in your quietness, your rest, your slowing breath, are exactly as you are meant to be. It isn't just science, it's meaning. Finding Ammonite tells us we are capable of finding beauty in faintness. We are persistent enough to uncover old secrets. We are connected to something vastly larger than ourselves. The universe is not distant. It is our home, and we are slowly learning its history like children gathering seashells from an endless beach. Ammonite is one such shell, spiraled, ancient, carrying stories older than Earth itself. Astronomy has always been a discipline of fragments. Even with the largest telescopes, the most advanced spectrometers, and the most powerful computational resources, astronomers do not uncover whole objects or events. They collect slivers of light, brief exposures, spectral lines, slow motions across fields of stars. From these scattered signals, they construct knowledge. The discovery of Ammonite is remarkable not merely because a new world was found, but because it was determined to be ancient and undisturbed. Its orbit has remained stable for billions of years, moving along the same stretched ellipse since the era when the solar system was a dense, chaotic disk of ice and rock. This stability transforms Ammonite into a kind of geological sample from space, preserving information about a time far older than Earth itself. Astronomers have often spoken of comets and Kuiper Belt objects as fossils of planetary formation, but sednoids belong to a deeper category of relic. They exist so far from the gravitational interference of planets that they preserve the dynamical environment of the solar system's earliest epoch with minimal disruption. Because of this, the physical and orbital properties of Ammonite have become invaluable evidence for reconstructing our cosmic history. Researchers are not merely curious about what the object is, but what it remembers. Most objects in the solar system have participated in a long history of interactions. Asteroids collided, broke apart, and reassembled. Comets repeatedly approached the Sun, shedding matter with each passage. Kuiper Belt objects experienced countless gravitational nudges from Neptune, shaping the belt's structure into its present resonant patterns. Ammonite's environment, by contrast, has been quiet to the point of isolation. At distances of 66,252 astronomical units, the gravitational force of the Sun is weak, and the influence of planets negligible. There are no collisions there, no dense populations of objects, no regular perturbations. It is a region where the solar system barely exists. This isolation is more than a physical condition. It is a data point. It implies that the object's orbital characteristics originated early, under circumstances that must have been dramatic enough to cast it outward, yet not so dramatic as to eject it entirely into interstellar space. The question arises, what kind of cosmic event is capable of producing an orbit this large, yet this stable? The earliest era of planetary formation was defined by migration, violence, and rearrangement. Protoplanets shifted position repeatedly, sweeping up material, colliding, and reshaping their trajectories. Smaller bodies, caught in their gravitational wake, were cast outward into more distant regions. This process created the Kuiper Belt and the scattered disk. These regions contain remnants of early solar debris, but they are populations shaped by disturbance, not preservation. Sednoids do not fit this pattern. Their orbits extend beyond the influence of planetary migration, but remain gravitationally bound. They are too distant to be part of the conventional scattered disk, but too stable to be random ejections. Thus, they represent a third category of solar system architecture, one that demands an explanation. For decades, the leading hypothesis centered on the gravitational influence of an undiscovered planet, Planet 9. If such a body existed, its mass could sculpt distant orbits through long-term, subtle interactions. Ammonite's orbit, however, complicates this possibility. Its orientation differs from that of other sednoids. It does not align with the presumed clustering that Planet 9 should produce. If a hidden planet is responsible, the mechanism must be more complex than initially conceived. Alternatively, the sednoids may encode evidence of a past that involved external forces, not internal ones. The Sun was not born in isolation. It originated in a stellar nursery, where hundreds or thousands of stars formed together from a collapsing molecular cloud. For tens of millions of years, these stars orbited within a cluster, occasionally approaching one another closely. A passing star, at the right velocity and distance, could exert sufficient gravitational influence to lift small bodies into distant, elongated orbits. Such interactions would have been more frequent during the solar system's infancy, when stellar density was high. Computer simulations have shown that single close encounters can restructure entire populations of objects, stretching them outward while preserving their coherence. This scenario explains several features of the sednoids: their elongated orbits, their extreme distances, their long-term stability, their small population. But more intriguingly, it explains why some sednoids might share characteristics, while others, like Ammonite, do not. If different objects were influenced to different degrees based on their initial positions, slight asymmetries in the encounter could produce divergent orbital orientations, a relic of a chaotic reshaping event rather than a smooth gravitational shepherding. In this view, Ammonite is not an outlier. It is a witness to history. Another hypothesis appeals to the possibility of a planet that no longer exists. During the early phases of formation, the solar system may have hosted additional large bodies. Some could have been ejected into interstellar space during gravitational interactions with Jupiter or Saturn. This process is not merely theoretical, it is expected. Models that replicate the architecture of the present solar system almost inevitably eject at least one primordial planet. The gravitational influence of such a planet could have reshaped the outer system, scattering objects into distant orbits before vanishing from memory. This is not science fiction, it is astrophysics. Planetary ejection is a natural consequence of multi-body dynamics. If such a body once existed, then the sednoids, Ammonite included, may be its legacy. Their orbits could be the fossilized imprint of a vanished world. Sednoids pose another challenge: statistics. With only 4 specimens known, the population is too small to support reliable statistical inference. Yet, their existence implies a larger, unseen population. In astronomy, detection is shaped by bias. objects are easier to find, when they are near perihelion, when they are not obscured, when they are in observable regions of sky, when their orbits align with survey strategies. The volume of space in which sednoids may reside is immense. The fraction we have sampled is tiny. The number we have detected is minuscule. Thus, any attempt to derive population estimates must contend with enormous uncertainties. And yet, even conservative models suggest that the sednoid population could number in the dozens, possibly hundreds, maybe thousands, extending outward into regions that have never been imaged, catalogued, or conceptualized in detail. Ammonite, therefore, is not merely a discovery. It is a hint, a window into a hidden architecture of space. Every science has its archive. Paleontology has bones. Geology has strata. Biology has DNA. Anthropology has ruins. Astronomy has orbits. The orbital parameters of objects in the solar system are not transient conditions. They are records of events, shaped by forces that acted millions or billions of years ago. Sednoids are particularly valuable because their orbits are historically inert. They have not been erased by planetary migration or collisions. Their trajectories preserve the gravitational environment of primordial time. To reconstruct events from these trajectories is an exercise in cosmic archaeology. It requires data simulation statistics, imagination, and patience, because the timescales of this domain exceed human experience. Sednoids do not record events of years or centuries. They record events of epochs. They remind us that the universe is not only large in space, but deep in time. The discovery of Ammonite invites a human response that transcends the technical. Rarity evokes emotion. To find one of 4 known objects in the solar system feels akin to uncovering a lost manuscript, an untouched burial site, or an ancient organism preserved in amber. But the rarity of sednoids is different from the rarity of human artifacts. It is not the result of disappearance. It is the result of persistence. These objects are rare because they are survivors, not remnants. They have endured not through preservation by design, but through simple absence of disturbance. They exist because nothing has happened to them. There is an odd beauty in that. In a universe defined by motion, violence, and change, sednoids represent stillness on a cosmic scale. Their survival speaks not to resilience, but to isolation. They endured because they were forgotten, and through that forgetting, they have become precious. Attempts to explain sednoids ultimately confront a deeper philosophical question. How does one reconstruct history when evidence is sparse, ambiguous, and probabilistic? Astronomers operate under a kind of epistemological constraint. They study systems that cannot be observed directly, events that cannot be recreated, and timescales that cannot be experienced. They work with the echoes of processes long finished. In this context, uncertainty is not failure. It is an inevitable condition. Every hypothesis must be resilient enough to withstand incompleteness. Ammonite forces astronomers to confront this uncertainty directly. Its orbit does not confirm a specific narrative. It destabilizes several. It neither proves nor disproves Planet 9. It neither confirms nor rules out stellar encounters. It neither validates nor dismisses past models. Instead, it reveals that multiple histories are consistent with the evidence, and that reasonable theories may coexist in tension. This is not lack of knowledge. This is science grappling with a universe that refuses to be simple. Ammonite is a world without atmosphere, weather, seasons, or geological activity. It is likely a cold assemblage of ice, rock, and organic compounds, preserved in a vacuum so complete that time has almost no effect. And yet, it is not merely an object, it is a record. Its orbit preserves the memory of a vanished epoch. Its physical composition preserves the chemistry of early matter. Its isolation preserves the silence of outer space. In this way, Ammonite transcends its modest size. It is a messenger from a time beyond history, from a world before worlds existed. The sednoids remind us that not all artifacts are shaped by human hands. Some artifacts are shaped by gravity, by collision, by stellar migration, by the slow drift of cosmic matter. And some artifacts simply endure. The discovery of Ammonite does not answer the question of how the outer solar system formed. Instead, it reframes the question. It reveals that the early solar system was stranger than models predicted, and that its remnants are scattered in regions where sunlight is weak, where time proceeds at glacial pace, and where the past has not been erased. Ammonite exists as a reminder of a forgotten era, preserved beyond interaction, beyond disruption, and beyond memory. It is a fossil not of life, but of environment, a relic of a cosmos that no longer exists. There is a region of space where the sun becomes almost a rumor. Its light stretches outward in all directions, but its strength diminishes with distance faster than instinct can predict. At 1 astronomical unit, the sun commands the worlds with an overwhelming pulse of heat and light. At 10 astronomical units, it weakens to a whisper, still enough to stir the atmospheres of giants but no longer decisive. Beyond 100 astronomical units, the sun becomes almost an abstraction, distant enough that photons act more like wanderers than agents, particles indifferent to what lies ahead. And yet, even here, the sun governs. This is one of the strange paradoxes of astrophysics. Gravity, unlike light, does not fade quadratically with visibility. It is not measured by radiance, color, or warmth. It is the architecture of motion, the foundation of orbits, and the silent law that shapes the trajectories of worlds. It stretches outward infinitely, diminishing in strength but never in authority. Ammonite exists in this paradoxical frontier, a place where gravity is weak but governance is absolute, a place where light is faint but motion is ordained by an invisible mathematics. This boundary is not empty. It is a vast domain of subtle forces, where the push and pull of gravitational fields unfold at speeds so slow that human lifetimes cannot track them meaningfully. The outer solar system is not a void. It is a theater of imperceptible dynamism, where time replaces energy as the engine of transformation. To understand such a realm demands patience, not the kind that waits for days or months, but the kind that spans geological epochs. Astronomy is built upon this patience. It is a science that treats time as both an enemy and an ally. It confronts the impossibility of witnessing events directly and compensates by reconstructing them from fragments that drift through space like fossils of motion. Ammonite is one such fossil. Its orbit, composition, and isolation are the product of physical laws that unfolded not in years, but in billions of years. It is a world carved by time itself. Far from the sun, temperature ceases to be a matter of weather or climate. It becomes a physical fundamental, an ambient condition dictated by this absence of energy. The region where Ammonite resides exists at a temperature just a few degrees above absolute zero, not because it receives no sunlight, but because it receives sunlight diluted to the point of irrelevance. In environments like this, matter undergoes a transformation. Ice becomes rigid as stone. Organic compounds freeze into molecular glass. Atomic motion slows until entropy becomes an almost theoretical concept. Objects in this environment do not erode by wind or water. They erode by radiation. Particles that strike their surfaces over millions of years, altering chemical bonds with glacial slowness. Cosmic rays do the work of sculptors, but with a pace that escapes intuitive understanding. Ammonite's surface has undergone these processes for longer than Earth has existed. The faint radiation that reaches it leaves microscopic scars, tiny fractions of energy deposited into molecules that cannot escape the cold. It is a slow evolution, but not a meaningless one. Over billions of years, cosmic radiation can darken ice, alter reflectivity, and change the spectral fingerprint of minerals. This surface, altered by time rather than motion, becomes one of the most revealing features an astronomer can observe. It is not a landscape of change, but of permanence. Every crater that exists on Ammonite's surface may have existed for billions of years. Every ridge may have been formed in an era when Earth was a sterile sphere of molten rock. From a human perspective, such permanence is difficult to conceptualize. We live within cycles measured in days and years. We age in decades. Civilizations rise and fall within centuries. But Ammonite is older than civilizations, older than continents, older than life. Its landscape is ancient not just by human standards, but by cosmic ones. In narratives about the solar system, attention gravitates toward the spectacular, the planets that dominate volumes of space, the moons with atmospheres or oceans, the storms that dwarf terrestrial weather systems, the rings that catch light in perfect arcs. Small worlds, especially those at extreme distances, rarely capture the imagination. They lack the scale to be majestic, the activity to be dramatic, the familiarity to be sympathetic. But in astronomy, size is not a measure of importance. Small bodies, particularly those that have remained undisturbed, are repositories of primordial information. A planet is a story that has been rewritten countless times, overwritten by heat, tectonics, erosion, and chemistry. A small world in deep space is a story that has barely been written at all. It is both beginning and end. Its isolation is not an accident, but an attribute born of dynamics. Worlds like Ammonite reside in a domain where encounters are exceedingly rare. They are immune to the collisions that remodel asteroids and moons. They are not subject to the gravitational turbulence that reshapes orbits in the inner solar system. Their solitude is not a lack of activity. It is a condition of preservation. Isolation becomes a mechanism of endurance. The universe, indifferent as it may seem, occasionally provides pockets of stillness, regions where the frenetic energy of cosmic evolution gives way to stability so perfect that it approaches stasis. These regions, though barren and cold, perform a role analogous to cryogenic vaults, preserving matter, structure, and motion across epochs. Ammonite is a beneficiary of this vault, but more importantly, it is a witness to its existence. To speak of the solar system as a coherent structure is to ignore its complexity. It is not a symmetric model with neat zones arranged by proximity. It is a distribution of matter across distances so vast that even metaphors strain to remain meaningful. Beyond Neptune lies the Kuiper Belt, a dense population of icy bodies shaped by a history of planetary migration. Farther still lies the scattered disk, where elongated orbits reflect the chaotic dynamics of early solar evolution. But past these regions lies something different, a population so sparse that it borders on hypothetical. This is the realm of detached objects, worlds whose perihelia are so distant that they have escaped the gravitational influence of Neptune entirely. Their existence implies a different formative mechanism, not scattering, not migration, not resonance, something earlier, something deeper, something else. Sednoids, including Ammonite, belong to this domain. Their orbits place them in a category that is neither theoretical nor fully understood, a liminal zone between the solar system and interstellar space. This architecture challenges the idea that planetary systems are neat, hierarchical arrangements. Instead, it suggests that planetary systems are the product of processes that include expansion, disturbance, scattering, capture, and occasionally, Serenity sednoids do not tell the story of stability. They tell the story of transition. They are markers of thresholds in cosmic structure, thresholds between the gravitational certainty of planetary space and the diffuse neutrality of interstellar medium. They exist not at the center of the solar narrative, but at its boundary. And boundaries often hold the clues that the interior cannot provide. The orbital stability of Ammonite seems improbable when imagined intuitively. How can something so distant remain gravitationally bound for billions of years? How can a force so faint maintain coherence across such distances? How can perturbations fail to accumulate over timescales so vast? The answers reside in mathematics rather than intuition. Gravity, although weak at large distances, is constant. It imposes constraints that are not energetic but geometric. The orbits of bodies are not shaped by momentary impulses, but by continuous subtle curvature. A small object in a distant orbit experiences gravitational force so slight that it barely alters its velocity. But because that force persists indefinitely, the object cannot escape unless it is given a profound energetic input, far greater than the soft disturbances it encounters. This phenomenon is counterintuitive. We are accustomed to systems where motion is arrested by friction, where forces dissipate abruptly, where stability requires active maintenance. But celestial systems are governed by different principles. Objects in motion remain in motion, unless acted upon strongly, and strong interactions are rare in the outer system. Stability, in this sense, is not a consequence of strength, it is a consequence of weakness. The outer solar system is stable because nothing happens there. It is the physics of neglect, not protection. The emptiness is not obstacle, it is mechanism. Every structure, physical or conceptual, has an edge, a border defined not by walls, but by diminishing influence. The solar system is no exception. Its edge is not where matter stops, but where governance fades, where the sun's gravitational rule yields to the galactic tide, where motion is shaped not by a single actor, but by a distributed environment. This region is not devoid of physics. It is governed by tidal forces, perturbations, resonances, and gradients so faint that time is the only instrument capable of revealing their agency. Objects that reside in this space, like Ammonite, are shaped by these forces, but not quickly. Their motions encode not instantaneous dynamics, but patterns accumulated across eons. To study such objects requires living in a paradox, recognizing that motion exists without visible effect, accepting that change occurs without narrative, acknowledging that history exists without witnesses. The outer solar system is not empty. It is slow. It is an archive of processes that operate on timescales so extended that they become invisible. The question is not whether anything happens there. The question is whether we can notice. Astronomers do not observe Ammonite as it is. They observe the faint echo of photons reflected from its surface. Photons that may have begun their journey hours before they arrived. In deep space, distance is indistinguishable from delay. Every observation is retrospective. Every measurement is memory. This is not merely a technical limitation, it is a philosophical one. Astronomy is a science without direct access to its subject matter. It reconstructs realities from delayed signals, partial data, and sparse information. It treats light as testimony, not presence. The outer solar system amplifies this limitation. The objects are faint. Their motion is slow. Their physical characteristics are subtle. Their behavior is cumulative rather than episodic. To draw conclusions from such evidence requires a mode of reasoning that is not statistical, but inferential. It demands an acceptance that certainty may not be attainable, but coherence might be. The study of Ammonite, therefore, is not merely observational astronomy. It is epistemology. It is the practice of constructing knowledge under conditions of radical scarcity. In a universe defined by collapse, combustion, collision, and entropy, stability may appear uneventful. Yet there is a profound elegance in systems that maintain shape across billions of years. Stability is not absence, it is persistence. Ammonite is not remarkable because it changes. It is remarkable because it does not. Its orbit is not dramatic. Its geology is not dynamic. Its evolution is not expressive. And yet, in its silence, it carries information that turbulent worlds cannot preserve. The universe reveals itself not only in its catastrophes, but in its stillness. Sometimes, the most profound stories are written not in heat, motion, and chaos, but in the patient geometry of endurance. Distance in the outer solar system is not merely a measurement. It is a condition of existence, a shaping force, a boundary that dictates how matter behaves. The distances involved are so extreme that everyday analogies collapse under their own inadequacy. Engineers can describe the span between planets in miles or astronomical units. Scientists can express it in light hours. Mathematicians can place it in coordinate systems. But none of these representations fully capture what it means to exist in a domain where motion unfolds across millennia. In human cognition, distance is relational. A horizon is where sight ends. A mountain is what stands between 2 points. A journey is measured in days or weeks, perhaps months at most. Yet, beyond Neptune, a single orbital path requires thousands of years to complete. The velocity is not slow in any physical sense, tens of thousands of miles per hour, but the scale renders that speed irrelevant. A world can travel faster than any object humans could construct, and still appear motionless for generations. This is where perception begins to fail. Human time cannot apprehend cosmic time. Human distance cannot intuit cosmic distance. But physics can. Physics remains indifferent to human limits. It describes a world not as it is experienced, but as it is governed. Ammonite travels in a gravitational field so attenuated that small accelerations accumulate slowly and uninterrupted. Its orbital period is not a cycle, it is a chronology. A single revolution marks a transition in planetary history, not in human life. It is possible that no single generation has ever lived to witness its movement in a meaningful way. Its pattern is invisible, not because it does not exist, but because we are too temporary to witness it. Astronomy, in this context, becomes not a study of present events, but a study of trajectories, of where objects were, of where they are likely to go, of how motion persists in a universe without urgency. One of the less intuitive aspects of the outer solar system is the economics of illumination. Light fades with the square of distance, a geometric principle with profound consequences. At 1 astronomical unit, sunlight is abundant, sufficient to warm oceans, drive photosynthesis, and illuminate landscapes with a brightness that defines our concept of day. But at 100 astronomical units, sunlight is reduced to 1/10,000th of its strength. At 200 astronomical units, its power becomes 1/40,000th. These are not incremental reductions. They are collapses, transformations of a life-sustaining force into a state of near absence. The idea that sunlight still reaches these regions may be technically correct, but it is functionally misleading. It does not illuminate. It does not warm. It does not drive chemistry or weather or climate. It is light that has crossed so vast an emptiness that it has become little more than cosmic residue. In such an environment, darkness is not the absence of light. It is a definition of space. It is a physical attribute, not a poetic metaphor. Astronomers must adapt to this condition. They cannot photograph distant worlds by capturing images, because there are no images to capture. Instead, they collect signals, photons that arrive in numbers so small that detectors must operate on the edge of sensitivity. A single pixel becomes a world. A flicker becomes evidence. A statistical deviation becomes revelation. To study a world like Ammonite is to acknowledge that observation is not an act of seeing, but of counting. Light, in this regime, is no longer experience. It is data. Motion in the inner solar system is familiar. Planets follow near-circular paths. Their velocities fluctuate, but remain stable. Their trajectories are defined by the dominant gravitational force of the Sun, modified by the predictable influence of neighboring planets. But the outer solar system does not obey these intuitions. Its orbits are elongated, so elongated that the standard notion of an orbit begins to lose precision. A sednoid spends the overwhelming majority of its existence at its farthest distance from the Sun, moving slowly through a realm where gravitational energy is minimal. The orbital eccentricity is not a quirk, it is a clue. It is evidence of a formative past that did not conform to processes. It suggests that these worlds did not arise in their present orbits, but were placed into them. This raises questions that reach beyond the conventional narrative of planetary formation. If Ammonite did not form where it now resides, then two possibilities emerge. It was moved outward by a massive gravitational event. It was captured from an external source. Both scenarios imply a history of disturbance, not stability. Yet the result is the opposite: long-term stability on astronomical timescales. This is the paradox of sednoids. Their existence implies chaos, but their current behavior implies serenity. In this, they resemble fossils of motion rather than relics of matter. Small worlds are fragile not because they lack cohesion, but because they lack protection. They have no atmospheres to blunt impacts, no magnetic fields to shield against radiation, no geological processes to erase scars. They are vulnerable to every collision, every cosmic ray, every bombardment of dust and debris. And yet, paradoxically, they endure. The outer solar system, for all its harshness, is also a refuge. Not because it is safe, but because it is empty. Collisions become rare, not because objects are durable, but because they are isolated. Chemical evolution becomes slow, not because materials are stable, but because energy is scarce. Radiation damage accumulates, but at a rate so slow that effects become geological rather than catastrophic. A small world that would be pulverized in the asteroid belt can persist in deep space indefinitely. Fragility, in this context, becomes compatible with longevity. It is one of the more surprising lessons of planetary science. In the realm of scarcity, endurance is easier than destruction. There is a misconception that objects in deep space are abandoned by gravity. In reality, they are imprisoned by it. They are not far from the Sun because gravity has weakened, but because early events imparted velocities that matched precisely the energies required to sustain eccentric orbits without escape. This balance is improbable because it is narrow. If early events had imparted slightly more energy, objects would have escaped the solar system. If they had imparted slightly less, objects would have remained close to the Sun. Instead, they occupy a region where motion is neither bound tightly nor free fully, a liminal state between possession and exile. These orbits are not the default outcome of a planetary system. They are the residual artifacts of rare trajectories. Their existence implies mechanisms that are no longer active. Early stellar encounters, planetary scattering events, ejections of massive bodies, migration episodes, transient resonances. The outer solar system, therefore, is not only a museum of matter, it is a museum of motion. The objects within it are not only old in age, they are old in trajectory. And trajectory may be the most durable artifact of all. Time in the outer solar system is not measured in seasons, but in epochs. The notion of year collapses when a single orbit takes millennia. Obliquity, rotation, and axial tilt may still exist, but they play no meaningful role. Patterns that define terrestrial experience, night and day, winter and summer, storm and calm, lose relevance in a physical regime dominated by duration rather than variation. This leads to a profound conceptual shift. Worlds like Ammonite do not experience time as a sequence of events. They experience time as continuity. Their surfaces do not record episodes. They accumulate conditions. Their evolution is not narrative. It is accretive. The timescales involved are so long that even when change occurs, it is absorbed into a longer texture of persistence. The radiation that alters molecules, the collisions that produce craters, the sublimation of volatiles. These are not events, but processes. Processes measured not in decades or centuries, but in spans of time that exceed the age of most terrestrial species. If a crater formed on Ammonite when dinosaurs walked the Earth, it would not be ancient there. It would be recent. If a surface feature formed when early mammals evolved, it would be very recent. If a structural change occurred during the rise of humans, it would be nearly instantaneous. Worlds do not change slowly because nothing happens. They change slowly because time in this environment is too vast for speed to matter. To study distant objects requires a form of empiricism that is not aggressive, but contemplative. It requires the willingness to interpret faint signals without haste, to build arguments from fragments, and to accept uncertainty as a condition rather than a defect. Astronomy at great distances is not based on direct observation, but on inference. It is built on spectra, albedo motion thermal profiles, dynamical models, statistical reasoning. Every conclusion must be provisional, not because evidence is weak, but because evidence is sparse. The difference is significant. Sparse evidence is not unreliable, it is incomplete. The study of Ammonite, therefore, demands a methodology that embraces incompleteness. It does not seek perfection of knowledge, but coherence of explanation. Science in this context is not the pursuit of certainty. It is the pursuit of intelligibility. The universe may not reveal itself fully, but it can reveal itself sufficiently. To exist at the boundary of the solar system is to occupy a category of being that is neither planetary nor interstellar. It is to exist in a continuum that challenges classification. Ammonite is not merely distant, it is distant by nature. Its identity is inseparable from its position. Its meaning is inseparable from its orbit. Its history is inseparable from its endurance. It exists as a transitional object between two gravitational regimes, the dominion of the Sun, the domain of the galaxy. Both forces shape its trajectory, but neither dictates it fully. It is bound, but loosely, governed, but gently, influenced, but not dominated. This intermediate condition gives rise to a philosophical question. Is Ammonite part of the solar system, or is it part of the galaxy that happens to be captured by the Sun? The answer may be both, or neither, or something new. Worlds at this distance do not belong to a system. They belong to a gradient. They exist not within a structure, but within a transition. Their essence is not substance, but location. If the inner solar system reflects the dynamism of formation, the outer solar system reflects the persistence of aftermath. Worlds that remain there have survived every disturbance, every collision, every cycle of migration. Their continued existence is not an event, it is a residue. To be a remnant is not to be trivial, it is to be foundational. Remnants preserve history in a way that complex systems cannot. Planets forget, moons erase, atmospheres conceal, geology overwrites, but the frozen worlds on the outskirts remember. Not in diaries, but in invariance, orbit composition structure, reflectivity, density, spin. These characteristics survive because nothing has occurred to change them. Stillness is not a lapse in evolution, it is a record of origin. The solar system is full of survivors, but few are as ancient, as isolated, or as unchanged as objects like Ammonite. They are not relics of habitability. They are relics of possibility. They show what existed before evolution, before complexity, before heat and time reshaped matter into worlds with internal histories. They are not the products of cosmic creativity. They are the products of cosmic restraint. The outer solar system challenges narrative. It resists interpretation in terms of goals, events, or milestones. It offers no climaxes, no turning points, no conflicts, no protagonists. It is a landscape defined not by activity, but by duration. This does not mean that nothing happens there. It means that everything that happens is subordinate to time. The physics of this environment is not dramatic, it is patient. The geology of these worlds is not expressive, it is persistent. The chemistry is not reactive, it is stable. Motion is not rapid, it is continuous. If the inner solar system is a story of formation, evolution, and transformation, the outer solar system is a story of endurance. Not endurance against adversity, not endurance through struggle, but endurance as the default outcome of distance. The vast regions beyond Neptune represent a cosmic regime where energy is scarce, interaction is rare, and change is slow. In such a domain, survival is simple, but meaning is complex. Objects like Ammonite do not answer questions about life, intelligence, habitability, or destiny. They answer questions about origin, structure, and persistence. They reveal the universe not as narrative, but as continuum. A continuum in which a time does not merely pass but accumulates. In which matter does not merely exist, but remembers. In which motion does not merely occur, but endures. The silent frontier of the solar system is not a boundary between worlds. It is a boundary between concepts, between what we think the universe should be and what it actually is. In the silent darkness beyond Neptune, the cosmos preserves what nearer worlds erase. In the inner solar system, planets are restless. They churn and twist, bury their histories beneath weather, tectonics, atmospheres, oceans. They recycle surface and substance alike. Memory is overwritten again and again until only fragments remain. But out in the deep, where light barely reaches and energy has grown faint through distance, worlds remain untouched by the momentum of change. There, the universe forgets nothing. Matter keeps its original shape. Ice preserves its original chemistry. Orbits maintain the curve they were given billions of years ago. Much of astronomy is an effort to reconstruct histories that have been erased by time. But the outer solar system does not erase. It accumulates. It records. It keeps. It is, in a sense, the cosmic archive, the place where the universe stores its early drafts, its raw materials, its first experiments in structure and motion, not because they are important, but because nothing ever happened to disturb them. This is one of the great paradoxes of cosmic evolution. The farther one moves from the sun, the less one discovers of life, but the more one discovers of origin. Life thrives in environments filled with complexity and energy, but memory thrives in environments defined by simplicity and scarcity. Life is dynamic, but memory is static. The inner solar system creates, transforms, destroys. The outer solar system preserves. And in that preservation lies a kind of truth the inner worlds cannot provide. To understand the objects now drifting in the cosmic night, we must imagine the solar system not as it is today, but as it once was, chaotic, violent, and catastrophically unstable. There is a temptation to picture formation as a graceful event, dust swirling into disks, colliding gently, aggregating into worlds. But the truth is more dramatic. The early solar system was a battlefield, a domain of violent collisions, sudden migrations, planetary cannibalism, and gravitational upheaval. Planets did not form quietly. They formed through conflict. Massive bodies plowed through the young disk, scattering smaller objects, ejecting some entirely, capturing others. Giants migrated inward, then outward, reshaping the trajectories of every lesser world in their path. If one could compress that chaotic epoch into a single cinematic moment, it would look nothing like the tranquil solar system we know today. It would resemble a storm of stone and fire, where collisions were as common as revolutions, and where nothing remained where it began. The survivors of that age fall into two categories: those who grew large enough to maintain internal change and thus erase their memories, those who remained small, distant, and dormant, and thus preserved theirs. Ammonite belongs to the second category, not because it was destined for preservation, but because it was not important enough to be destroyed. The giants fought over the center. The debris fled to the edge, and in that exile, memory was born. One of the most surprising discoveries in modern astronomy is that the outer solar system, despite its apparent emptiness, is a region of astonishing stability. Not because gravity is weaker, but because interactions are fewer. The environment is so sparse that objects rarely collide, rarely migrate, rarely undergo catastrophic alteration. There is no atmosphere to erode surfaces, no heat to drive volcanism, no oceans to carve landscapes. There is only time. This is why so many objects in the Kuiper Belt and beyond still exhibit the same orbital characteristics they acquired during the earliest stages of solar system evolution. They are architectural remnants, fossils of motion rather than fossils of biology. Their orbits encode a record of ancient gravitational events, the passage of rogue stars, the migration of giant planets, the scattering of primordial disks, the ejection of massive bodies, the reshaping of resonance structures. These events are not hypothetical. They are written into the architecture of the system. Orbit becomes testimony. Eccentricity becomes evidence. Inclination becomes memory. Where geology preserves material, orbital mechanics preserves history. The great chronological irony of the solar system is this: the outermost worlds, which change the least, reveal the most. They tell us how the story began, not how it ends. Small worlds in the outer solar system are fragile in every physical sense. Their gravity is weak, their internal structure porous, their composition delicate. A strong impact could obliterate them. Radiation could chemically alter them. Internal heat could disrupt their structure. And yet, they endure. The paradox is easily misunderstood. Fragile objects do not survive because they are durable. They survive because the universe forgot about them. If the asteroid belt is a city, crowded, noisy, and prone to collisions, then the outer solar system is a deserted continent where nothing encounters anything. There are no impacts because there are no neighbors. There is no erosion because there is no weather. There is no tectonics because there is no heat. Fragility thrives not in safety, but in emptiness. Objects like Ammonite are not resilient. They are irrelevant in the most cosmically beneficial way. They survived because nothing happened to them. They survived because they mattered to no process, no planet, no star. Preservation, in this context, is not a triumph over adversity. It is the absence of adversity. Worlds that dominate the center are doomed to transformation. Worlds exiled to the edge are doomed to preservation. In this, exile becomes endurance. There is a growing view among astronomers that the solar system is not merely a collection of worlds, but a machine. A dynamical system designed by physics, optimized over billions of years to maintain stability. It is a machine that consumes disorder and produces structure. A machine that channels energy, redistributes momentum, and preserves angular momentum with mathematical precision. Its architecture is neither accidental nor arbitrary. It is the inevitable outcome of physical law acting over deep time. The planets are not scattered randomly. Their arrangement reflects the minimum entropy configuration of a multi-body system. The small worlds of the outer solar system, the ones that appear insignificant, are essential to this architecture. They act as buffers, stabilizers, absorbers of excess momentum. They are not particles. They are components. Every small world plays a role in maintaining the gravitational balance. It does not do so intentionally. It does so automatically because physics demands it. In this light, Ammonite is not merely a relic. It is a functional artifact. A small, ancient, silent gear in a machine built not by design, but by inevitability. The universe does not design machines, it becomes them. There is a certain philosophical grief in realizing that most of the universe is empty. Stars occupy a tiny fraction of space. Planets occupy a fraction of that. Life occupies a fraction of a fraction of a fraction. The overwhelming majority of existence is void. The outer solar system embodies this truth with brutal clarity. There are no colors there, no landscapes, no weather, no seasons. There are only rocks and ice, drifting in a silence so complete that sound cannot exist. And yet, that nothingness is not meaningless. It is structure, it is duration, it is memory. The inner solar system is the realm of events. The outer solar system is the realm of being. We seek meaning in activity because activity resembles life. But the universe is not defined by activity. It is defined by existence. Rocks drift not because they choose to drift, but because motion is built into the fabric of space-time. The universe does not need drama to be profound. Its depth lies in the fact that nothing is wasted, not even emptiness. A world that has done nothing for billions of years is not dull. It is honest. It reveals the universe as it truly is: vast, patient, indifferent, and enduring. We often speak of memory as a biological phenomenon. Neurons storing experiences, minds forming narratives, organisms preserving identity. But the universe preserves memory without mind, without intention, without consciousness. Memory is not a function, it is a property. Matter remembers, stone remembers, ice remembers, orbit remembers, not as stories, not as images, not as meaning, but as patterns of structure and motion. A crater is memory. A chemical signature is memory. An orbital inclination is memory. Not memory of experience, but memory of cause. And so, when we observe Ammonite, we are not observing a passive object. We are observing a memory system, one that has preserved the initial conditions of solar system formation. In philosophy, memory is the preservation of past perception. In physics, memory is the preservation of past energy. In biology, memory degrades with age. In astronomy, memory strengthens with age. The older a world is, the more of its history it retains. Not because it protects it, but because it cannot escape it. Time does not erase history, it hardens it. Ammonite is not ancient. It is timeless, because nothing has intervened to impose time upon it. It is difficult for humans to grasp processes that unfold over millions of years. We are creatures of hours, days, months, perhaps decades. Even a century represents an extreme span of consciousness. Geological time is already beyond us. Astronomical time is unimaginable. The solar system operates on timescales that dwarf cognition. A world may complete a single orbit in the entirety of human history. A surface feature may remain unchanged for the entire lifespan of humanity as a species. A chemical signature may endure for billions of years without modification. Time, at such scales, is not sequence. It is medium. Things do not happen in time. They happen through time. The objects of the outer solar system move with an unhurried precision that borders on beauty. Their paths are not rushed. Their changes are not urgent. Their existence is not pressured by scarcity, predation, competition, or decay. They are the product of cosmic patience. Not the patience of intention, but the patience of indifference. The patience of physics. The patience of the universe itself. If one could stand on the surface of a distant object like Ammonite, ignoring the impossible cold, the lack of atmosphere, the mechanical vacuum, one would witness a kind of solitude that does not exist anywhere on Earth. The sun would not be a disk of light. It would be a star, bright, brilliant, but small. Planets would not be visible. Moons would not rise. There would be no horizon. Only shadows cast by the distant sun across a terrain of frozen rock. And the silence would be absolute. Not quiet, but soundless, because silence is the absence of medium, not the absence of noise. There is a loneliness inherent to such worlds, but it is a loneliness without suffering. There is no longing in stone. There is no grief in ice. Solitude is only painful in creatures who need connection. A world does not need anything. A world simply is. The outer solar system is not lonely. It is solitary. It is the solitude of windless deserts, of deep oceans, of mountaintop snow. Magnified beyond comprehension. Not tragic, not empty, not abandoned, just indifferent, just enduring, just present. There is something both terrifying and beautiful in the realization that the universe does not require observation to exist. Ammonite did not need to be discovered for it to matter. It did not need to be named for it to have meaning. It did not need to be witnessed for it to be real. The universe is not a performance. It is not narrative. It is not metaphor. It is process. For billions of years, Ammonite followed its path without recognition. It drifted in darkness without audience. It accumulated memory without interpretation. It did not know it existed. It did not care. Its existence is not contingent upon awareness. It is contingent upon physics. And yet, something remarkable happens when humans discover such a world. The universe acquires witness. Matter acquires metaphor. Motion acquires narrative. Silence acquires language. Humans transform what is into what means. The universe does not become beautiful until someone sees it. It does not become mysterious until someone questions it. It does not become profound until someone contemplates it. We are the interpreters, not of meaning, but of meaninglessness. The universe offers existence. We offer significance. And between these two, something like poetry emerges. When we speak of legacies, we usually mean intentional consequence. Things created, preserved, remembered on purpose. But cosmic legacy is unintentional. It is the residue of events so vast and impersonal that they could not have been otherwise. Ammonite is a legacy not because it contributes to something, but because it testifies to something. It is not the result of design. It is the remainder of accident. A piece of matter drifting endlessly, carrying within its orbit the memory of a universe that was once young. It is not majestic. It is not heroic. It is not sacred. And yet, in its long endurance, it embodies a lesson humans rarely consider. Not everything that lasts was made to last. Not everything that persists was meant to persist. Not everything that remains was preserved. Sometimes survival is simply the absence of interruption. Sometimes permanence is just the consequence of insignificance. The universe is not sentimental. It does not preserve what is meaningful. It preserves what is stable. Meaning is a human concern. Stability is a cosmic one. Matter does not endure because it deserves to endure. It endures because nothing acts upon it to destroy it. The inner solar system is a realm of violent events. The outer solar system is a realm of violent time. Events are rare, but time is long. And time, even in silence, transforms. Not through motion, but through exposure. Cosmic rays, micrometeorites, vacuum sublimation. Even when nothing happens, something happens. But it happens slowly. So slowly that change becomes indistinguishable from permanence. The surface of Ammonite does not tell a story of cataclysm. It tells a story of endurance, not triumphant endurance, not heroic endurance, passive endurance. The endurance of matter that has outlived planets, stars, species, and civilizations. Not because it could, but because it never had reason not to. It is tempting to ask what lessons Ammonite offers, as if the universe crafted wisdom into stone. But there are no messages here. The universe does not write parables. The universe writes physics. The only lessons we can draw are those we invent ourselves. And yet, invention is not deception. It is interpretation. We observe endurance and we infer stability. We observe silence and we infer solitude. We observe ancientness and we infer significance. We observe the universe and we see ourselves. Not because the universe reflects us, but because we reflect ourselves onto it. In that sense, Ammonite becomes metaphor, not because it wishes to be, but because we need it to be. We do not look at the stars to understand them. We look to understand ourselves. The universe is not a mirror. It is a surface upon which we project meaning. And yet, some meanings feel true, even if they are human. For most of human history, the universe was incomprehensible. The night sky was a mystery, filled with lights that moved in ways that defied explanation. Worlds beyond Earth were unknown. Time was shallow. Space was small. Only recently, in the last heartbeat of cosmic time, have humans gained the ability to understand distances, measure ages, calculate orbits, decode spectra. We have not eliminated mystery. We have relocated it. As knowledge expands, ignorance does not diminish. It becomes deeper, more subtle, more refined. The mystery of the modern universe is not, what is that light in the sky? It is, what is the long history of this world that has existed for billions of years without witness? The mystery is not, are we alone? It is, what does it mean that we are capable of asking? Wonder is not the opposite of knowledge. It is its outcome. The more we learn about the universe, the more mysterious it becomes, not because we understand less, but because we understand more than we can comprehend. Ammonite does not solve mystery. It deepens it. Not because it hides answers, but because it reveals questions we never thought to ask. If one were to summarize the outer solar system in a single word, it would be this: calm. Not peace. Peace implies conflict overcome. Not silence. Silence implies an absence that might be broken. Calm is something else. Calm is a state that simply is. The outer solar system is calm because it does not change quickly enough to disturb itself. It is calm because nothing competes, nothing predates, nothing hunts, nothing flees. Calm because time is so vast that motion becomes indistinguishable from stillness. Calm because existence is not threatened. The inner system is full of drama, storms, collisions, geology, life, extinction. The outer system is full of duration. Not life, not narrative, not struggle, just existence. Still, steady, enduring. And in that endurance, something like beauty emerges. Not the beauty of brilliance, but the beauty of peaceful inevitability. In the end, the story of Ammonite is not a story of adventure, discovery, or progress. It is a story of time. Time that does not care about intention. Time that does not reward a purpose. Time that does not require awareness. Time that simply is. We search the universe for meaning. We search the universe for life. We search the universe for reflection. But sometimes what the universe offers is not reflection, but contrast. A reminder that existence does not require experience, sensation, or narrative. A reminder that matter endures without witness. A reminder that worlds drift unobserved, untouched, unchanged, for longer than life has existed on Earth. A reminder that the universe is not built for us. We are built within it. And if there is one truth that arises from the silent journey of a distant world, it is this. The universe does not need to be alive to be profound. It does not need to be conscious to be beautiful. It does not need to be purposeful to be mysterious. The outer solar system, with its frozen worlds and endless night, is not empty. It is full of time. And in that time lies the oldest memory in existence. A memory without mind, without narrative, without meaning, but with endurance. An endurance that will continue long after we are gone. An endurance that will outlast every civilization, every species, every world that knows itself. An endurance that belongs not to life, but to the universe itself. In every era of human history, there has been a horizon, a line between what is known and what is not yet understood. Long ago, that horizon lay only a few miles from home. A traveler could stand on a hill, look outward, and see the boundary between the familiar and the uncertain. Today, that horizon lies far beyond the reach of the eye, beyond the limits of sensation, beyond even the domain of intuition. It lies in the cold, unlit spaces between worlds, places where sunlight arrives not as warmth or radiance, but as mathematics. Beyond Neptune, beyond the Kuiper Belt, beyond the scattered disk, there lies a region not of objects, but of unknowns. It is not a frontier in the traditional sense. It is not a landscape waiting to be mapped. It is not a treasure waiting to be claimed. It is a question, stretched across space. We do not know how many worlds exist there. We do not know what shapes they take. We do not know what histories they preserve. But we know this much. The universe does not build emptiness without purpose. Even silence holds information. The outer solar system is not empty. It is simply waiting to be understood. And humanity, in its short, flickering existence, has only just begun to listen. When we talk about exploring distant worlds, we imagine spacecraft, shining vessels crossing impossible distances, touching ancient surfaces, returning stories of alien landscapes and frozen oceans. But the truth is less romantic and more profound. The next era of exploration will not be defined by travel. It will be defined by perception. We will extend our senses through technologies that do not resemble current instruments. Technologies that translate invisible wavelengths into meaning. Interpret subtle patterns into history. Transform nearly noise-level data into revelation. Future telescopes will not simply see, they will infer. They will reconstruct 3D structures from faint, scattered photons. They will decode chemical fingerprints from spectral whispers. They will model atmospheres from fluctuations measured over months. They will visualize surfaces from variations in reflected light. They will do what eyes cannot, and they will do so from unimaginable distances, perhaps hundreds of astronomical units away, with no need for proximity. The irony is striking. The more distant the world, the more interpretive our science must become. We will not touch those worlds. We will translate them. The next chapter of astronomy will not be written by explorers, but by algorithms. Not by footsteps, but by inference. Not by journeys outward, but by journeys inward, into data, into structure, into probability. And somewhere within that complexity, we will find clarity. Not because the universe makes itself simple, but because we become capable of understanding its complexity. There are dreams, quiet, theoretical dreams, of sending a probe into the outer darkness. Not a flyby, not a brief visit, but a pilgrim of metal and memory, designed not for return, but for witness. Such a craft would leave the inner solar system on a path of no return, crossing the boundary between sunlight and starlight, entering a domain where energy is scarce, where communication is faint, where time is measured in generations rather than years. Its engines would not roar, they would whisper. Ion drives, solar sails, nuclear propulsion. Technologies conceived not for speed, but for endurance. A craft launched today would arrive in the realm of sednoids long after its designers, its builders, and perhaps its civilization have disappeared from Earth. We would not send such a mission to learn something quickly. We would send it as a gesture toward persistence, a declaration that curiosity can survive even when the curious do not. We would send it because we are mortal, and because the universe is not. We would send it because there is something deeply human in reaching for things we will never see. Where we once carved names into stone to survive time, we will one day launch instruments into space to survive extinction. Not because the universe will remember us, but because forgetting ourselves would be worse. There will come a time, measured not in centuries, but in cosmic eons, when the Earth no longer remembers us. Cities will dissolve, languages will vanish, stories will be erased, species will rise and fall, continents will drift, oceans will evaporate, the surface will forget. It must. Geology is not a keeper of secrets, it is a destroyer of evidence. But the outer solar system does not forget. It does not erase, it does not recycle, it does not heal, it preserves. Long after Earth has buried every trace of humanity beneath tectonics, volcanoes, sediment, oceans, and erosion, long after all that is left of us is dust and isotopes, the outer solar system will remain unchanged, silent, cold, ancient, and drifting through that darkness, without awareness, without purpose, will be the archives of our existence. Probes that outlived their makers, signals that outlasted their languages, fragments of technology slowly drifting toward absolute zero echoes of mathematics embedded in metal and code. We will not endure in myth or memory. We will endure in debris. Not because the universe values us, but because the universe does not destroy things it does not notice. Our future legacy may not be glory. It may be geometry. It may be motion, orbits, trajectories, a long-lasting record of our curiosity, not our identity. Humanity may vanish, but our questions might not. There is a philosophical question at the heart of cosmic exploration. Do we explore the universe, or do we explore ourselves? When we map distant worlds, we are not just recording landscapes and orbits. We are recording the structure of possibility. We are learning what physics permits, what time transforms, what matter becomes, what systems evolve into, what complexity emerges from simplicity. And hidden within these discoveries is a more intimate truth. The universe is not made to be understood, but it is understandable. Not by accident, not by miracle, but by structure. The same laws that govern atoms govern galaxies. The same patterns that build snowflakes build stars. Complexity is not chaos. Meaning is not anomaly. Order is not coincidence. The universe is legible, not because it wants to be read, but because its grammar is physics. We are not writing the story, we are translating it. And somewhere in that translation lies the ghost in the machine. Intelligence, awareness, inquiry, interpretation, consciousness. Not cosmic consciousness, not universal intelligence. Just this. A species that looked at darkness and tried to understand it, not conquer it, not illuminate it, interpret it. There will come a time, far beyond our lives, beyond our species, beyond our planet, when the sun begins its final transformation. Its hydrogen will dwindle, its core will collapse, its outer layers will expand, Earth will die, the inner planets will burn, the outer planets will warm, the solar system will change shape. The worlds we know will become the worlds we knew. But the distant objects, the sednoids, the exiles, the fossils of the solar system, will drift outward, unbothered. They will not melt. They will not burn. They will not be consumed. They will outlive the sun, because they are not dependent upon it. Their energy is the energy of inertia, motion perpetuating itself across time. Their destiny is not collapse, but escape. They will drift away, not because they choose to, but because nothing holds them. And long after the sun has faded, long after the planets have fractured and cooled, long after entropy has undone complexity, these distant worlds may still exist, not as habitable, not as meaningful, but as trace evidence of a system that once was. The solar system will end. The universe will not mourn. But the outer worlds will endure, silent, cold, drifting toward a horizon that has no center. They will not remember us, but they will remember physics. There is a question older than science, older than history, older than language. Why do humans look at the night sky? Not just for navigation, not just for prediction, not just for curiosity, but for something deeper, a sensation that borders on longing. We gaze upward not because we expect answers, but because we carry questions. We seek not certainty, but perspective. We want to understand the universe, not to master it, but to locate ourselves within it. We do not fear darkness. We fear insignificance. And yet, paradoxically, the universe offers an answer. Significance is not given. It is created. Meaning is not found. It is constructed. The cosmos does not tell us who we are. We tell ourselves who we are, and then we project that story onto the stars. We are not small because we are physically small. We are vast because we imagine ourselves vast. We are not insignificant because the universe is large. We are significant because we can contemplate largeness. The universe is not a mirror. But reflection is the only way we know how to see. As this world, Ammonite, Sedna, the unnamed fragments of the deep, continue their motion through space, their story does not climax, resolve, or conclude. There is no ending, because endings are artificial, and the universe is not. The universe does not conclude. It does not resolve. It does not narrate. It only continues. Even death, whether of stars, planets, or species, is not conclusion. It is transformation. Matter does not disappear. Energy does not vanish. Structure does not dissolve into nothingness. It shifts. The future of the universe will not be defined by brightness, but by faintness. Not by heat, but by cold. Not by activity, but by duration. And somewhere in that duration, far beyond human comprehension, the remnants of worlds like Ammonite will still drift. Not alive, not aware, not meaningful, but real. And that reality, that quiet, enduring existence, is its own kind of narrative. Not a story we tell, but a story told by time. Not a story about purpose, but a story about persistence. Not a story that needs witness, but a story that endures witness. Because the universe does not require meaning, but it permits it. And humanity, brief, fragile, luminous, uses that permission to create beauty.